Hello students, have you ever wondered how a simple RTL code written in Verilog becomes a real chip inside your mobile phone? How does this logic turns into metal layers? How do millions of transistors get physically arranged? And how does timing constraint get controlled at nanometer scale? Welcome to the backend physical design. In the front end, we design the brain of the chip, but in the backend, we build its body. This is where we convert a synthesized netlist into an actual physical layout, placing standard cells, building the clock tree, routing metals, connecting, fixing timing, eliminating noise, and finally generating the GDS file that goes for fabrication. So in this video, we will clearly understand the complete RTL to GDS backend flow in the step-by-step, very simple and powerful way. Before entering into the session, please subscribe our channel. Yeah, in the backend side, there are 10 stages. First, let's see what all the stages available and what are the purpose of those stages. The first stage is import design. In this import design, the synthesized gate level netlist, technology files, libraries, timing constraint, and IO pads are loaded into the physical design tool to start backend implementation. The next stage is floor planning. Floor planning is the place where chip size and core areas are defined. Here, large blocks like SRAM and IPs are placed, and IO pin locations are decided here, and space planning is also done for smooth routing in the floor planning stage. The next stage is power planning. In this power planning, power distribution network is created using power rings, stripes, and mesh to deliver stable VDD and VSS across the entire chip. The next stage is placement. In the placement, millions of standard cells are arranged inside the core area in an optimized way to reduce wire length and improve timing. The next stage is clock tree synthesis, CTS. Here, a balanced clock network is built by inserting buffers so that the clock reaches all flip-flops at nearly the same time. The next stage is routing. In this routing, metal wires are drawn using multiple metal layers to connect all placed cells according to the netlist. Yeah, the next one is post-routing simulation. In this post-routing simulation, here the output we get after the routing must be equal to the output we got after the post-synthesis simulation and in the RTL simulation. Here, the timing analysis is performed after routing to check the setup and hold violation considering wire delays. The next stage is physical verification. In this, DRC and LVS checks are done. The DRC, design rule check, is the one in which layout is checked against manufacturing rules like minimum width, spacing, and layout constraint. In the LVS, the physical layout is compared with the original netlist to ensure both are identical. Next is post layout simulation. In this post layout simulation, the final verification is done with extracted parasitic effects to ensure the chip works correctly in the real silicon condition. The final one is GDS2 generation. The final verified layout is exported as a GDS file where it is sent to the foundry for the fabrication, that is tape out. The next, we are going to see what are the tools used to perform this physical design. We know in the physical design, we do import design, flow planning, power planning, placement, CTS, and routing. In Cadence tool, all these are performed using Innovus, and in the Synopsys tool, it is performed using IC Compiler 2. Now, in this flow, we are going to see the Cadence tool. We are going to use everything in the Innovus. Yeah, when we start the back-end physical design, the tool needs several mandatory files from the front-end team. So the many files from the front-end team and Foundry are got, and it is processed in the import design, and it is given to the back-end side to do the process. So now let us see what all the files used. The first one is gate level netlist, that is .v file. This we are getting it from the front-end synthesis, and this tells the tool what cells to place and how they are connected. This is the logical circuit that will be physically built. And the next one is technology file .tf. This we get it from the foundry. This defines manufacturing rules like metal layers, rules, spacings, and with constraints. The next one is logical library, that is .lib file. This also we get it from the foundry, and this provides timing and power models of each standard cells. This is used for timing optimization and STA during placement and routing. The next one is physical library, that is .left file. This also we are getting it from the foundry. This gives cell size, height, pin positions, and blockages. Helps the tool place cells correctly on the chip floor plan. The next one is timing constraint, that is .stc file. This we get it from the front end team. This defines clock frequency, IO delays, false paths. And this guides the tool to meet record timing performance. The next one is QRC, a parasitic text file. And this also we get it from the foundry. This provides RC values of metal layers, and it is used for accurate delay calculation after routing. And the next one is cap table. This is also we are getting it from the foundry. This gives early stage wire capacitance data for better timing estimation before full extraction. And next one is MC setup file. This we process in the backend side. This defines multiple PVT corners and operating modes to ensure chip works under all conditions. And the next one is input output paths.io files. This we get it from the front end team, and this IO paths are special physical cells placed at the boundary of the chip that allows the chip to communicate with the outside world. Now, after getting all the files from the front end team foundry, we will process in the import design, and we will get output like this. That is, after importing all the files, the tool doesn't magically create a chip. First, it creates empty chip boundary. Look at this. This is the empty chip boundary. And around the edges, you can see IO paths. Here, the IO paths and VDD VSS supplies are placed. The one thing which we have to keep in mind is, for every 5 to 6 signals, we need to have a pair of VDD supplies. The center region is the core area where millions of standard cells will soon be placed. Right now it looks empty, but this is where the real physical design journey starts. So after importing all the files, we get like this, and this will be sent to the backend part, that is for the flow planning. Since we are doing it in the cadence, we are going to save it as .enc file. Yeah, now let's start the flow planning. This is the blueprint of the chip. Flow planning is the first physical design step in the VLSI backend. It is the stage where chip size is defined, core area is decided, major blocks like SRAM, IPs, macros are placed, IO pin locations are fixed, and routing spaces planned. It is like designing the layout of a house before construction begins. If the flow planning is weak, everything after this becomes difficult. And if the flow planning is strong, timing, power, and routing becomes easier in the later stage. Now let us see the diagram. Look at this. This is the overall chip size. This chip size is decided in the flow planning, and this is the core area. The core area is also decided in the flow planning. And the next important thing is the major blocks like SRAM, hard IPs, ROM, PLL must be placed properly in the earlier stage itself, because it is difficult to move those in the later stage. So the planning of this must be proper. If it is not placed properly, they create routing blockages and they affect the timing heavily. So placing is very important. And the next one is during placing all these blocks, the routing space must be planned properly, because the later stage it should not affect the routing. And next, it gives the IO pin locations. It properly places the IO pin. So this is also done in the flow planning. After doing all these, the utilization planning is also done in the flow planning, and the ideal utilization range is 65 to 75%. This utilization, it is equal to standard cell area by core area. Why this utilization is important means the balanced utilization, it is the key for successful routing. So everything should be planned properly in the flow planning stage, and this is done in the flow planning, and it is saved as .enc in the Innovus for the later stage. Yeah, the next one we are going to see is power planning. Power planning is the process of designing a power distribution network to deliver VDD and VSS to every standard cells, macros and IP blocks in the chip. Without proper power planning, even a perfectly designed chip will fail. Why this power planning is critical? Because in modern chips, we have billions of transistors, high switching activities, multiple voltage domains, and tight power budget. If power is not distributed properly, IR drop occurs, voltage fluctuations happen, timing failure increases, electromigration damages the metal, and chip may fail in silicon. So this power planning ensures stable voltage, reliable operation, and long chip lifetime. Now let's see the diagram. Look at here. In this diagram, the three things in this power planning, it plays a major role. One is power rings or core rings, and power stripes and power rails. Look at this core ring. Core rings are created around the core. Look at this. Here the core rings are created. These rings get the power from the pads and it supplies it to the power stripe. So what does this power stripe do? These power stripes on both ends connects to the core ring. These power stripes are always created in the top metal layer, and these stripes supply the power from the core ring to the power rails. So what does this power rails do? These power rails connect VDD and VSS supply to the standard cells inside. So the power distribution must be done in such a way that it must not affect in the later point of time when we are making the tape out. So this power plan does it perfectly. Yeah, now we are going to see placement in the physical design, where millions of cells find their exact location. Imagine having 5 million blocks, and you must arrange them perfectly so that timing meets, power is low, routing is possible, and chip area is optimized. This process is done using this placement. Placement is the process of placing all the standard cells inside the core area. We have already placed the macros in the flow planning itself. Now we are going to place logic gates, flip-flops, buffers, inverters, and combinational cells inside, so that the main goal is to minimize the wire length, meet timing, and avoid congestion. And this is done here. And let's see the diagram. Look at this. This is our core area, and we know power ring, IO pins, everything we have already seen. In this core area, we must place millions of cells properly. That placing is done in this placement. Look at this diagram. The standard cells are placed. You see how it is placed here. And after placement and optimization, finally it looks like this. And this file, we are saving it in the NOS to proceed to the next step. The next is clock tree synthesis. Balancing time across millions of flip-flops. Imagine 5 million flip-flops in a chip. All must receive the clock signal at almost the same time. If it is not receiving, setup and hold violation occurs and chip failures. That balancing act is done using this clock tree synthesis. Clock tree synthesis is the process of distributing the clock signal, inserting clock buffers and inverters, building a balanced clock network, and minimizing the clock skew. Delivering clock to all sequential elements with the controlled delay is the CTS. What problem does CTS solve? This solves clock skew and clock latency. Clock skew, it is the difference in clock arrival time between two flip-flops. If skew is high, setup failure occurs and hold violation occurs. CTS minimizes skew. And clock latency, it is the time taken from the clock source to reach flip-flop. Too high latency affects timing badly. CTS controls latency carefully. So this CTS tool builds the tree-like structure, inserts clock buffers, adds inverters if needed, balances path delays, and reduces skew and performs the operation. Let us see the diagram. Look at this. This is the first one without the CTS. Then look at this. This CTS is doing everything in a balanced manner. See, all the clock signals received in the saved time. So this is the process of CTS. The next stage is routing. It is connecting millions of cells without crossing rules. In the placement, we arranged millions of cells. All those cells must be connected without shortcuts, without congestion, without timing failure. That complex wiring process is done using routing. Routing is the process of connecting all placed cells using metal layers, following design rules, ensuring timing and signal integrity. What does this routing connect? This routing connects standard cells, flip-flops, macros, IO pins, clock networks, and power networks. Millions of nets must be routed properly, and this is done using this routing. In this routing, we have global routing and detailed routing. The global routing gives us a rough path planning, and it divides the chip into routing grids and it estimates congestion. Whereas detailed routing, it exact metal wires are drawn and follows strict design rules and adds wires between layers. And now let's see the metal layers. Metal layers are conductive layers used to connect transistors and cells physically inside a chip. That is, they act like a road in a city, carrying signal and power across the chip. Without this metal layer, no signal movement, no clock distribution, and no power delivery. So we can tell that if there is no metal, no chip. And next one is design rules in routing. Routing must follow minimum spacing, minimum width, VR rules and metal density rules. If this is not following it properly, DRC errors occurs and manufacturing failure occurs. Routing must be clean and rule compliant. And after doing all these process, next we are going for post routing simulation to check whether our routing output is correct or not. Next one is post routing simulation, the real true check of your chip. Imagine you designed the RTL, you synthesized it, you placed cells, routed millions of wires. Now the biggest question is, will the chip really work after manufacturing? That is where the post routing simulation comes in. It is the final functional verification of your design after routing is completed. Here, this post routing simulation must be equal to post synthesis simulation and the RTL simulation. Whatever we have simulated in the RTL, the same result we must get in the post routing simulation also. If it is correct, we proceed to the next step. Yeah, after completing the post routing simulation, we are entering into the physical verification. That is, we are going to check it. Physical verification is done in Caliber Virtuoso. In this, two types of checking is done. One is design rule check, DRC. Another one is layout versus schematic, LVS checking. The design rule check is the one verifies whether the layout follows the manufacturing rules given by the foundry for a specific technology node like 28 nanometer, 7 nanometer, 5 nanometer, etc. Every foundry like TSMC, Samsung, Intel Foundry gives thousands of rules such as minimum metal width, minimum spacing between wires, overlap rules and density rules. Even if one metal line is too close, DRC error occurs. And if a wire is too small, DRC error occurs. So, a physical design must be done in such a way that it must satisfy the DRC rule. And in DRC rule, we do block level DRC, antenna check, dummy fill, and chip level DRC. After completing all these, and if our errors are zero, we go for LVS, that is layout versus schematic. DRC checks geometry, LVS checks connectivity. LVS compares the original Verilog netlist versus the extracted layout netlist. That is, both must be equal. If it is properly equal and matching, and if there are no any errors, we can proceed to the next step. If we are getting LVS error, we have to do some modifications in the physical design. We have to go back to the previous steps. We have to find where the mistake is, and then we have to rectify it. Once after clearing the DRC and LVS only, we can proceed to the next step. Now the final stage is post layout simulation. It is where the final verification is done with extracted parasitic effects to ensure that the chip works correctly in the real silicon condition. After doing this, look, this is the final GDS2 file. This is the tape out which we are giving to the foundry for fabrication. Today, we have traveled through the heart of VLSI physical design, from netlist to flow planning, power planning, placement, clock tree synthesis, routing and sign-off. Backend flow is not just connecting wires. It is the transformation of logic into silicon reality. Here, every micron, picosecond and milliwatt matters. Backend design teaches us precision, optimization, and it teaches us responsibility. So remember, front end creates intelligence, backend gives it life. And you can practice and do all these, and you can make your own chip. If you want to know how to do TCL script, how to make IO paths and constraint files, you can just follow us in our next videos. Thank you.